Hi guys, today I'll be studying about uh, again once again operating systems. Yeah, I had read up to this one critical section problem and how to address it in the morning. So I have to read about conditional variables and semaphore for thread synchronization and concurrency. So this is one of the concepts I have to study about. So let's again study about critical section problem and how to address it. So a critical section is a part of program where shared resources are accessed and modified. Part of a program where shared resources are accessed or modified. Now, if you think critical section is the memory location, it is wrong. Critical section is the part of a program where shared resources are accessed and modified. Like there will be two lines of code where we are going to use same shared where we are going to use same variable or same file or same device. So the those parts of the code becomes critical section. So if we say clearly, critical section is a part of a program where shared resources such as variables, data structures, or hardware devices are accessed and modified. Because these resources can be accessed by multiple threads or processes simultaneously. Okay, since these resources since these resources can be accessed by multiple threads or processes simultaneously, it's crucial to ensure that only one thread or process can execute the critical section at a time to prevent data inconsistency and race conditions. So these resources uh, these shared resources can be accessed by multiple threads and processes at a time. So we have to somehow manage that shared resources uh, in such a way that there will be no inconsistencies. This line is saying that because these resources can be accessed by multiple threads or processes, it's crucial to ensure that only one thread or process can execute a critical section at a time. Only one thread or process can execute the critical section at a time to prevent data inconsistency and race conditions. So before going to the down part, what is a race condition? Let's guess what is a race condition. Mm, so when okay, we know this is something about critical section and shared resources. So so critical section of the part means many to a program where shared resources are being accessed and modified. So let's say three threads are trying to access the shared resource and they are going to modify it. So we have to modify it in an order. Let's say A, B, C are the threads uh, which are accessing those shared resources. Now we want them to access and modify in some order. Let's say we want to modify either shared resources A in the order of A, B, C. Since it's a multi-threading environment and concurrency, due to concurrency, it may happen that while executing, it may happen that CPU may switch CPU may start executing these instructions in between these instructions before completely executing A's instructions. So it may happen that it may happen that B will update the shared critical section part before A. So this leads to data inconsistencies. So this is called race condition. Like there is a shared resource and these threads are racing to access those shared resources. So which may leads to data inconsistencies if not managed properly. Now let's read this. Process synchronization techniques play a key role in maintaining the consistency of shared data. Process synchronization means how managing threads in such a way that they are operated on a shared resources properly in a required in a specified order. Process synchronization means okay, managing threads in such a way that they can access shared resources in a specified way in order to maintain consistency across the shared resources. Critical section. Critical section refers to the segment of code where processes or threads access shared resources. The code where shared resources, where processes and threads access shared resources such as common variables and files and perform write operations on them. And since threads execute concurrently, any process can be any since process or threads execute concurrently, any process can be interrupted mid execution. Like between execution, it may happen that our CPU starts executing another thread. This may lead to, if it is not managed properly, this may lead to inconsistencies in shared data. Major thread scheduling issue. Okay, now comes the race condition. A race condition occurs when two or more threads can access shared data and they try to change it at the same time. Okay, so read operations are okay. These are all read operations are also not okay, because if we want to if we want to read first and then update later, and if CPU switches to another instruction sequence, like another instruction, let's say first CPU starts executing that instruction sequence which says read, but in between, before reading the operation, as a time quantum expires and it starts executing another sequence which it says update the critical section. Then after coming to the read section again, the our data is already updated. So when we read the data, when we read that data, we read it wrongly. So this may leads to this is bad. What happens? It leads to errors or unwanted results. Occurs when two or more threads occurs when through two or more threads can access shared data and they try to change it at the same time. They try to modify it at the same time. Because the thread scheduling algorithm can swap between threads anytime. Okay, before I was saying CPU may starts executing another thread, right? Who makes that transition? Thread scheduling algorithm may allocate CPU to another threads, because the thread scheduling algorithm can swap between threads at any time. You don't know the order in which the threads will attempt. You don't know the order You don't know the order in which the threads will attempt to access the shared data. Okay, we don't know the order in which the threads will attempt to share the access the shared data. Therefore, the result of the change in data is dependent on thread scheduling algorithm. The result of the change in data is dependent on thread scheduling algorithm. Okay, that shared resources data is dependent on the result of the shared data is dependent on result of the change in data depends on thread scheduling algorithm. That means both threads are racing to access change the data. Solution to how can we stop race condition? What we can do is uh, we can make critical section an atomic operation. Like we make that we uh, make critical section we may execute in so we will execute that thread in one instruction cycle. We somehow execute that thread. We will make sure that that thread is executed in one CPU cycle. That's one thing. We make sure that that thread is executed in one cycle. This can be done using mutex, mutual semaphores or mutex. This can be done using mutual exclusion, using locks. Semaphores. Can we use simple flag to solve the problem of a race condition? No. Why? Why can't we use simple flag variable to solve that problem of race condition? Let's say we will initialize a flag variable and we set it to 1 and we start executing. And if mm, if one process, let's say two are coming, and then first one wants to change the share access the shared data, we will keep mm, when we try to access the data, we will set that flag to we will say to that flag, hey, I am accessing this shared resource, so make sure that no one accesses this. What if CPU switches before keeping the um, saying it to the flag variable? So this may lead to some inconsistencies. So major difference between PCB and TCB is that PCB has memory info, whereas TCB doesn't have to store worry about memory. This is a classic operating system question, and it tests whether you really understand synchronization of race condition. Let's carefully go through it. No, we can't really solve race condition. It's just a simple flag variable. Race condition happens when two or more processors or threads access share data concurrently, and the results depend on the order of execution. Period mutual exclusion. Only one thread in critical section at a time. In fact, to show whether the critical section is occupied, the problem that check consider flag equals to 0 and then is not atomic. Thread A checks sees flag equals to 0, then thread B checks at the same time also sees flag equals to 0, both set flag equals to 1 and critical section together. Hmm. When two threads to enter the critical section at once, proper synchronization requires atomic operations of constructor and busy waiting. Okay, what's other issues with the flag? Threads keep looking on the flag. Threads keep looking on the flag. What does that mean? Mm, hmm. No fairness. One thread could have the flag star in the other. I'm thinking light keeps looking the flag. Threads keep looking on the flag. Let's say thread A comes and sees this and it says flag equals to 1 and it enters critical section. Now thread B comes and sees, okay, he's in the critical section, I won't enter. After in the second step, uh, this thread A sets its flag to 0 and again it tries to and again it tries to enter critical section by checking flag equals to 0 and it says yeah I'm open. Again it continues. Now the second thread will come and ask again, is someone there, and it says yes again, and it will after next operation it may update. I'm thinking it like that. Let's ask what explain these things clearly. PHP works. explain these things clearly. The threads keep checking the flag in a loop while it's waiting for entry into the critical section. Instead of imagine two students wanting to use a library book. Instead of going for a walk and coming back later, the second student just stands outside the library door, staring until the first student is done. Busy waiting. There is no guarantee that threads get settled. One thread might always grab the flag first. The threads would stop. It's constant. Busy waiting for awareness. Mm-hmm. Mm-hmm. Peterson's condition is larger, but for two process threads. Mutex, locks. Locks can be used to implement mutual exclusion and avoid race condition by allowing only one thread. Mm, by allowing only one thread to access critical section. We can solve race condition with mutexes and locks. Locks can be used to implement mutual exclusion and avoid race condition by allowing only one thread to access critical section. Disadvantages are deadlocks may happen. One thread has acquired the lock, other threads will be busy waiting. What if thread that has acquired the lock dies? Then all other threads will be waiting. Race condition did no starvation. When multiple threads are processed, try to access the shared resources simultaneously. It lead to inconsistent or incorrect results. Incorrect result. This is known as race condition deadlock. If two or more threads are waiting, if two or more resources, if two or more threads are waiting indefinitely for each other to release resources, deadlock occurs. Program to halt starvation. When a thread is never able to enter the critical section, Okay, sorry, I got distracted from this, so that's why I stopped. When a thread is never able to enter a critical section, when a thread is never able to enter a critical section because other threads are constantly accessing it, starvation happens. Conditional variables and semaphores for thread synchronization. Mm, primitive, okay. Primitive means that's the main part of synchronization. Part of synchronization. Main, definitely. Conditional variable is an important thing. Synchronization that lets the thread wait until a certain condition occurs. Okay, conditional, one of the most important thing in process synchronization that lets the thread synchronization that lets the thread wait until a certain condition occurs. That lets the thread wait until a certain, okay, lets the thread, okay, the thread will wait until a certain condition occurs. Works with a lock. With conditional variables works with a lock. Thread can enter a wait state. The thread can enter a wait state only when it has acquired a lock. When a thread enters the wait state, it will release the lock and wait. Okay, enters the wait state, it will release the lock and wait until other thread notifies that the event has occurred. Once the waiting thread enters the running state, it again acquires the lock immediately and starts executing. Not clear. Thread can enter a wait state only when it has acquired a lock. Let's say there is a critical section and thread can enter a wait state when it has acquired a lock. When a thread enters the wait state, it will release the lock and wait until another thread notifies that the event has occurred. Sorry, I again got distracted. I was thinking about some timings. So thread synchronization in Java similar languages that use monitors like we are talking about threads that use locks and methods like wait and notify. Lock, only one thread can hold it at a time, ensure mutual exclusion. Puts a thread into a waiting state until someone notifies it. Wakes up one waiting thread so it can try to continue. Thread acquires the lock. Suppose thread A enters a synchronized method lock. That means thread A has the lock. No other thread can enter this block until A is done. Thread calls wait. Thread A says I can't proceed right now. I'll wait until someone tells me to continue. Means thread A releases the lock. Important, otherwise no one else could ever notify it. Could ever notify it. Now the thread A releases the lock. Thread B or some other thread can acquire it. Thread B does its work and eventually calls notify or notify all. Thread A gets notified. Thread A moves from waiting to runnable state, but it cannot run immediately. First, it must reacquire the lock before continuing. Thread A continues execution. Once it gets the lock back, the thread A resumes data execution right after the wait call. There is one special book in the library. Only one student can read it at a time. Student A takes the book. Yes, oh, I need some notes before I can continue. I'll wait. So A gives the book back and sits in the waiting area. Student B comes, takes the book, finishes their part, tells A, hey, notes are ready. But before reading, A must grab the book again. So what if B changes the content of the book? Mm, Release lock, wait until condition becomes true. beam process beam enter synchronizer lock. Only I can touch the shared data at this time. Like yes, is condition invalid, so it calls. Wait, what way does this? Thread P acquires the log. We can modify the shared data. Condition become true. We to use conditional variables to avoid busy waiting. What is busy waiting? We have just read about busy waiting. So what is busy waiting? Busy waiting means it should check share shared semaphores synchronization method. An integer that is equal to number of resources. Multiple threads go and execute critical section concurrently. Allows multiple program threads to access the finite instance of resources, whereas mutex allows multiple threads to access a single. Okay, mutexes helps us in maintaining a single resources among multiple threads. Okay, mutexes helps us in maintaining a single shared resources among multiple threads. Okay, whereas semaphores helps us in maintaining multiple resources among multiple threads. Okay, that's the difference. Mutexes helps us in maintaining single shared so you are so among multiple th threads, whereas semaphores maintains a semaphore maintains multiple shared resources, multiple threads. Shows that only one thread can access the critical section at a time. Only one thread only can enter the room section binary lock. A signaling mechanism that uses a counter to its binary semaphore and receiver works just like a mutex. Thread in critical section counting semaphore allows up to n threads to access shared resources simultaneously. So a counting semaphore is what you are thinking of using multiple shared resources. Only one thread can access a resource at a time. Binary is also just the same as mutex, but it can be used for signature counting semaphore. Allows multiple threads to access a resource. Mm-hmm. Allows up to n threads to access the shared resources simultaneously. Only one thread can access the critical section. Mutex ensures that only one thread can access the critical section. Whereas a semaphore, binary semaphore ensures that up to n threads can access the shared resource simultaneously. Mutex is a lock that allows only one thread to access a resource. Mutex is a lock that allows only one thread to access the resource at a time, whereas a semaphore can allow multiple threads to access a limited. Whereas the semaphore can allow multiple threads to access a limited number of. So what is the use of mutex when there are binary semaphores? That's the question. One thread to access a resource at a time, whereas a semaphore can allow multiple threads to access a limited number of instances. A single thread to enter a critical section. And semaphore allows multiple threads to like critical section. be used to control access to a given resource consisting of a finite number of instances. Be used to control access to a given resources to a finite number of instances. Okay, finite number of instances, finite number of resources. There are resources, then finite number is multiple threads. To overcome the need of PC needed for can modify the definition of the wait and signal semaphore operations. When a process executes the wait operation and finds that the semaphore value is not positive, it must wait. However, rather than engaging in busy waiting, the process scar block itself. The block operation places a process into a waiting queue associated with the semaphore, and the state of the process is switched to the waiting state. Then control is transferred to the CPU scheduler. We access to just executes the wait operation and finds the rather than being in the busy waiting and wasting CPU cycles. We keep that the thread process in the waiting queue associated with the semaphore in the state of the process. Then control is transferred to itself so the process to execute a process. So what will we do to overcome busy and waste CPUs will keep waiting queue. To execute the process that is blocked waiting on a semaphore S should be restarted when some other process executes a signal operation. The process is restarted by a wake operation, which changes the process from waiting state to ready state. The process is then placed in ready queue. Process executes signal operation. Mm, mm, Now comes the main philosopher problem. Okay, we have five philosophers and um, five spoons, and they are trying to eat. Now, they everyone needs two spoons to eat, and if everyone picks one spoon, it will be there will be a deadlock. So we need some mm, methods to avoid deadlock in this case. What we can do is we only pick forks, forks or spoons. We pick spoons only when both of the spoons are available. Mm. They spend their life just being too just thinking. They sit on a five chairs, center of a table, thinking straightly. Philosopher thinks he doesn't interact with others. It instead when a philosopher family, he tries to pick up the full core solution to him. He can pick one fork at a time. One can't pick up a fork if it's already taken when philosophers thought releasing forks. Solution can be given using semaphores. Each fork is a binary semaphore. The philosopher calls wait operation to acquire a fork, release fork by calling signal. Although the semaphore solution makes sure that no two layouts are eating simultaneously, but it couldn't still but it could make sure that no two layouts are eating simultaneously, but it could still create deadlock. But like every one will pick one side fork and calls wait operation. Suppose all Five philosophers become 100 at the same time, and each picks up their left fork. Then all four semaphores will be zero. When he tries to grab his right fork, he will be waiting forever. We must use some methods to avoid deadlock and make the solution work. Allow at most four philosophers to be sitting simultaneously. Allow at most four philosophers to eat simultaneously. Allow a philosopher to pick up his forks only if both forks are available. To do this, you must pick them up in a critical section atomically. Let's say again same five processes and five resources. Each process needs three resources to complete execution. So at a time, how many processes can work? Hmm, yeah, how many processes? We can allow two people, right? At max, we can use three. If we keep three people, one may take one, two, two. That case seems bad. Odd even rule. Hmm, odd even rule. Philosopher picks up his left fork and then his right fork, whereas an even philosopher picks up his right fork. I'm odd even then his left fork. Since only semaphores are not enough to solve this problem, we must have some enhancement for the solution. Deadlock. After finishing the all dying philosopher problem, we are studying about these deadlocks. Okay, let's see about our channel analytics. We want analytics. If we click analytics, okay, deadlock. These are easy. Mm, this is deadlock prevention, deadlock avoidance. Next, MMT. MMT is a beautiful thing. MMT, memory management. Deadlock part one. In multi-programming environment, that means we load multiple programs to the CPU process to the CPU at a time. We have several processes competing for finite number of resources. Processes request resource or if it's not available, take another process enters in a waiting state. Sometimes the waiting process is never able to change its state because the resource it has requested is busy forever. This condition is called deadlock. Deadlock is case where two or more processes are waiting for each other indefinitely. Uh, Two or more processes waiting for each other. Waiting for each other. Waiting indefinitely for each other to release their resources. It also is deadlock is a bug present in synchronous synchronization method. In deadlock process never finish executing and the system resources are tied up, preventing other jobs from starting. Example of resources: memory space, memory, CPU cycles, files, logs, sockets, IO devices, etc. Single resource can have multiple instances of that. CPU is a resource and the system can have two CPUs. For a process that utilize a resource request the ICE free locket, else wait till it is available. Use release resource instance and make it available for other process. Deadlock necessary conditions. Okay, there are four necessary conditions for deadlock. These are should hold simultaneously. These four conditions should simultaneously hold in order for and these are the necessary. These are the mandatory. These things are these things. Okay, these four conditions are the necessary conditions, not sufficient conditions. Even though these four conditions are uh, these four conditions hold simultaneously, then there may be a case that there may be case that that deadlock will never happen. So if deadlock happens, these four conditions will be there. So the converse is not true. So what are the four conditions of four necessary conditions for deadlock? Mutual exclusion. Only one process at a time can use the resource. Okay. Mutual exclusion of resources. Only one process at a time can use the resource. If another process requests that resource, the requesting process must wait until the resource has been released. Okay, only one process can access the resource, and if some other process is requesting for that resource, it has to wait. It has to wait until the currently you until wait must wait until the resource has been released. Until the resource has been released. Hold and wait. The process must be holding at least one resource. Okay, mutual exclusion. Mutual exclusion means only one process can Only one process at a time can use the resource. If another process is trying to, if another process is requesting a resource, it has to wait until the resource has been released, until the resource has been released. Hold on, wait. A process must be okay. A process must be holding a resource and, and wanting to acquire additional resource currently. Okay, the process must be holding a resource and it is waiting for some other resource which is holding by other process. No preemption. Resource must be voluntarily released by a process after completion of execution. If there is a prevention after some time, that this process release the resource, so other process may access it. So there should be no preemption. Means so the resource will be released only after the completion of execution. Means resources should be released by the process only after the completion of its execution. Completion of execution. Circular wait. A set of waiting process must exist such that if a set of let's say two processes are in if mm, some processes are said to be in deadlock, they have to be circular wait. That means one process is waiting for other processes for the resources which are being held by the another process. Methods for handling deadlock. Handling handling deadlock. We can prevent deadlocks. I somehow deadlock happen. We have to avoid prevention deadlock avoidance. Okay, deadlock happen and we have to avoid deadlocks, ensuring that the system prevent or avoid deadlocks. Okay, preventing means making sure that we try to avoid. It may happen. We making sure that the deadlock will never happen. Avoidance means it may happen, but we have to deal with it, ensuring that the system will never enter a deadlock state. Allow the system to enter a deadlock state, detect it, and recover it. There are three ways of handling deadlocks. Not the problem altogether, pretend that deadlock never occurs in the system. If you break any one of them, deadlock can't happen. Deadlock prevention, deadlock avoidance, deadlock detection and recovery, deadlock ignorance. Practical approach. Health deadlocks are rare and hard to predict. Cost of prevention. You say if a deadlock happens, engage the process manually. Kaufman conditions. Necessary conditions for deadlock. Mutually exclusive. Only one process can use a resource at a time. One process can use a resource at a time. Mutual exclusion. Mutual exclusion, then hold and wait. Process has to be process holding at least. The process has to hold one resource and this way and waiting for other process resources which have been held by another process. No preemption. Just one resource wait for others. Resource cannot be possibly taken away. Circular wait. And there are 4 ways to handle deadlocks: deadlock prevention, deadlock avoidance, deadlock detection and recovery, deadlock ignorance. Design the system so at least one of 4 conditions never hold. Example, no hold and wait. A process must request all resources at once. Deadlock avoidance: don't prevent but avoid entering unsafe states. Banker algorithms. Okay, we will only grant resources but keep the system stable. Requires process to declare maximum resource needed. But you want, then we need to know how many resources and how much time the process need to hold the resources. Violence detection that happen but detect them, fix them. Detection use wait for process. Methods to handle deadlock prevention. We make sure that one of the 4 necessary conditions will never happen. avoidance. Use shortcut flag codes to stay in safe state. Detection, recovery, hello, then detect via wait for graph and fix. Mm, Wait for graph. It not do nothing. Using no servers. You can handle prevention avoidance and recovery or simply by ignoring depending on system required. Mm, General resources. Each branch has to request and allocate or request and be allocated also. So the process to request resource can be it has it can request any additional resources after it. After all the resources that if a process is holding some resources that can be immediately allocated to it, then all the resources the process is currently holding are preempted. The process will start only when it can regain all resources available. Okay, if a process requests some resources, we first check whether they are available. If yes, we allocate. If not, we check whether they are allocated to some other process that is waiting. The desired resources are in the requesting process. schedule process and its sources allocation such a way that the deadlock never occur. The safe state is a safe state is safe. The system can allocate resources to each process in some order and still avoid deadlock. The system can allocate resources to each process in some order and still avoid deadlock. The system is in safe state only if there exists a safe sequence. The operating system cannot prevent process from requesting resources in such a way that it is not necessary that all unsafe states are deadlocks. An unsafe state may lead to a deadlock. The main key of the deadlock avoidance method is whenever the request is made for resource, the request must only be approved only in the case of result. If we give the resources to the required resources to the requesting process, we will check that after giving these resources, our state leads to our states leads to a safe state or not. The system must determine whether allocating these resources will leave the system in a safe state. If yes, then the resources may be allocated to the process. If not, then the process must wait till other processes leave. Deadlock detection. Systems have a deadlock detection can be done. Systems haven't implemented deadlock techniques, then they may employ deadlock detection. Then recovery technique. Single instance of each resource type. Wait for graph. Recovery from deadlock process termination. Preempts resource process. Done by process termination or resource preemption. Comes the memory management technique. What should I do? Should I watch videos or let's see how much length the video is. So I have 5 hours. Hmm. Okay, guys, I will can do time pass if you want. We'll stop for now because I can't start this thing right now because it takes time to eat. Okay, if possible, I will try to stream after my dinner because I have to watch videos because I have read this a lot way back. It will be easy for me to understand, but I have to. This is 5 hours. It will be very. From this, I will finish this by tomorrow morning. Yeah, I had a good day. Like I was able to solve some problems in DSA in Java. So I have learned about hash maps and about some little how to stream links and strings are mutable in Java. So we use string buffer